All right, Natural Logarithms, Unit 9, Day 5. So what is E? Well, you should have watched that little video about kind of where E comes from. I know a lot of that stuff we haven't really learned yet, but E is an irrational number that has an approximate value of 2.71828, blah, 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 blah. And E occurs as the base of exponentials and logarithms, and that describe real-world scenarios. So it pops up in the real world a lot. Kind of weird, but it's kind of like pi, just pi is more well-known, and then E. Okay? So exponential functions with a base E are called natural base exponential functions. So like f of x equals e to the x, that's a natural base exponential function. Okay, logarithmic functions with base e are called natural logarithms. So like that would be log base e of x. And this pops up so often. There's even a button on the calculator for this. It's abbreviated, sorry, I cannot talk right now. It's abbreviated ln of x. So natural logarithm of x. That's how I kind of think of it, like logarithm natural of x. Natural logarithm, okay? And let's just get into this. So we're going to write an equation in logarithmic form. So e to the x equals 24. That's the same thing as log base e of 24 equals x. So that's ln of 24 equals x. For b, that would be log ln of x equals 9. ln of 72 equals x plus 5. Then if we're changing these back to exponentials, well, ln of x, that's the same thing as log base e of x. Then you can change that, so that's e to the 58th power equals x. E to the x power equals 6. E to the 32nd power equals x minus 9. Okay? And then condense and expand these. You guys can do these. Here's the answers to them. If you get them wrong, ask in class, and we can go through them and explain how to get the right one. Okay? Now, solving these, you solve them the same way you solve logarithms. I mean, ln is a logarithm, but if you have ln of 4x minus 27 and ln of 15 minus 2x, cancel those ln's and you get 4x minus 27 equals 15 minus 2x. Just solve for x. You get 6x equals 42. X equals 7. Okay, and then we have to check for extraneous solutions. Do this every single time. So I'm going to plug 7 back in and just make sure I don't get a negative number. I don't, so that's good. And 7's our answer. Cool? Let's do this one. So we first need to combine them so we only have one ln on both sides. So that's going to be ln of 72 divided by 4 and ln of 6 times a minus 2. So that's ln of 18 equals ln of 6a minus 12. Those cancel, and you get 18 equals 6a minus 12. Add the 12 over, 30 equals 6a, divide by 6, a equals 5. Then we just have to double check that. So then we have 5 minus 2 equals 3, and we're good. Okay? For this one, a little bit different. ln of 8x equals 2. That's the same thing as log base e of 8x equals 2. Change that to an exponential. So you have e to the second power equals 8x. Well, e, you can put that into your calculator. It's the second and then the division key. That's e. And e squared is 7.3891 approximately equals 8x. Divide by 8. And you get x equals 0.9236. Check for extraneous solutions, so plug that in, you get 7.3891, and we are good. Okay, for this one, let's change it to a logarithm. So that's going to be log base e of 57 equals x. Well, log base e is ln, so ln of 57. There's an ln button. It's right underneath the log button, so just put that in your calculator. You get 4.0431. Voila. Okay. Same thing here. First, we want to get rid of that 5, so divide by 5. And you get e to the 4n equals 19. change that to a logarithm. So ln of 19 equals 4n. Put ln of 19 into the calculator. You get 2.9444. Approximately equals 4n. Divide by 4. You get 0.7361. And then you can check that, but we're good. Okay? So ln's, that's basically just log base e. That's all it is. Now let's get into some applications. So exponential growth. So when something grows exponentially, so it gets big really fast. The formula for that is y equals a, and then parentheses 1 plus r to the t power, where a is your initial amount, r is the growth rate, and t is time. Okay, and that's usually in years. It can change based on like what problem it is though. So let's do one of these problems. It says the original value of an investment is 1,800. If the value has increased by 7% each year, write an exponential function to model the situation, then find the value of the investment after 15 years. So let's circle what we know. We know that the original value was 1,800. The value increased by 7% each year. And we need to find the value after 15 years. So my initial amount is 1,800. My growth rate is 0.07 because that's 7%. And my t is 15. And then I'm just going to plug that in, put that entire thing into my calculator, and you get 4,966.26 cents. Okay? Save example B for class. Now exponential decay, same equation, we just have a minus sign in between. So y equals a, 1 minus r to the t power. A is the initial amount still, r is the growth rate, t is time. So let's look at this one. An investment of $12,000 is losing value, so that tells you it's a decay, at a rate of 4% each year. Write an exponential function to model the situation, then find the value of the investment after 9 years. So the initial amount is $12,000. The growth rate is 4%, but it's decreasing by 4%. And then it's after 9 years. So A is 12,000, R is 0.04, T is 9. Plug that in, and you get 8,310.41 cents. Cool. Save that other one, and let's just get into compound interest. Compound interest is basically the same, but your investment is compounding every month, or whatever it is, whatever it may be. It could be every month, it could be every week, it could be once a year, it could be twice a year, so on and so forth. So that's y equals p. They changed it to p. I don't know why. That's just a universal thing. But p times 1 plus r over n to the nt power. P is the same thing as A. It's your principal, but that's really just the initial amount. Okay? R is the annual interest percentage today. What? N is the number of times compounded, and T is time. So R is like your rate, whatever it is. Okay? So it's the same as it was before. Now let's look at this. So Boston deposited $12,000 into an account that earns 8% interest. How much money will she have in 5 years if the interest is compounded quarterly? So it's deposited. She has $12,000. That's her P value. It earns 8% interest. So that's the percentage of interest she earns. That's your R value. We want to know how much money she'll have in 5 years, so 5's my time, and then it's compounded quarterly. So quarterly, that's 4 times every year, because there's 4 quarters in a year. So A is 12,000, R is 0.08, N is 4, T is 5. Plug that into the equation, put it in your calculator, and you get 17,831.37 cents. So after 5 years, when she deposited $12,000 into the account to begin with, I'm really struggling, sorry. $12,000 to begin with, 5 years later, it grew to $17,831. Cool? That'd be nice, right? Okay, let's look at this one. So Bruno took out a 6-year loan for $25,000 to purchase a boat at a 4.5 interest rate. If the interest is compounded monthly, what will he have to pay total over the course of the loan? So it's a 6-year loan, $25,000, 4.5% interest, and it's compounded monthly. So my p-value is 25,000, r is 0.045, and that's how many times it's compounded. If it's monthly, there's 12 months, so it's 12. And then t is 6. Plug that in, put it in your calculator, and you get $32,732.58. So he took out a loan for $25,000, purchased this boat, ended up paying $7,732 more because of the interest. Okay? Let's do one more. So an investment account pays 3.9% interest compounded semi-annually. If $4,000 is invested into this account, what will the balance be after 12 years? So 3.9% semi-annually, $4,000 to begin with, and the balance after 12 years. So my P is 4,000, my R is 0.039, N is 2, T is 12. Plug that all in, and you get $6,358.48. Okay? Save those last two for class, and remember to take the quiz. I will see you guys later.